All right, folks, let's get started. Take a seat, everyone. Still, there are seats available in the front. Okay, so before we come to today's topic, data abstraction, as you can see here, there was one slide that I still owed you from last week. Remember that we were talking and could everyone please listen and stop talking? Everyone, please. Thank you. So remember we were talking about structures where we can combine, for example, 3 integers into a larger object that we call a structure. Generally, guys, you could do me a favor if you're coming late. It would be better if you, right? And that applies to you as well. If you're coming late, can you listen? If you're coming late, please use the door upstairs, just to minimize disruption. So we can collect individual variables into larger objects, which we call structures. Here we have defined a date type, a time type, and then a speeding ticket that contains some of these previously defined structures. And I showed you how you would use the newly created structured type with the name date t to declare variables of this type, and then you can use the dot notation to access the individual fields in this structure. And the last thing that I wanted to show you is, just like with standard simple data types, you can also use these more complex structured data types as parameters to a function. Here's one that takes a date. It consists of these 3 integers as an argument. So as usual, you say what type your argument is, and then you give it a name. This is the variable, which will then be a copy of the structure with which you call this function, and then you can access the individual fields just like you would normally do. And here's an interesting function that returns whether a given date is a leap year or not. Again, you get a date, and then you decide whether it is divisible by 4, but not by 100, or by 400. And if that complex Boolean logical condition is true, then, as we know, this counts as a leap year. So that completed the introduction into these basic data types and the basic structured data types like arrays and structs. And just to reiterate, if you want to read on more on any of the specific topics that we talked about in this section, then you will always get hints as to which particular section to look at. That completes the introduction to basic data and control structures in C, and we will now consider our very first specific topic to data structures and algorithms, and we will see how to handle this in C, namely the concept of data abstraction. So this is what we're going to talk about today. First of all, I want to remind you that we have that weekly problem set, and as you would have seen, there is now a sample solution available, really only sample solution. If you wrote your own program and it produces the expected output but looks slightly different from what I provide, then of course that would be correct also. If you didn't find the solution, just click on the problem set again and you will see that it has changed. It now comes with a link to answers at the end of every question. So this I will always provide every Monday after the lecture. Now in this lecture, as I said, we will be talking about abstract data objects and data types. They are so important that they are abbreviated as ADTs, abstract data types. To read more about it, look at the slides and look at these two textbooks, Moffat and Sedgwick, and the corresponding sections. And as an outlook for next week we will continue talking about abstract data types, and we will see that in C they are implemented with the help very often of so-called dynamic data structures. And these will be the chapters. If you want to do some pre-lecture reading, then it might be a good idea to look at these chapters. So we will be starting with data abstraction, or looking at data abstraction today, but at the beginning, there's one other thing that, as a light introduction to today's lecture, one other thing that I wanted to teach you, namely something nerdy that every good computer scientist should know. Now, suppose you're sitting in a lab, or you're sitting together with your study group, and you're looking at some code, which looks like this. You want to ask a question about the code, but you're not sure how to refer to these characters that occur in here. For example, this character here. And also, you really don't want to sound like a non-computer scientist. You want to sound like a nerd. Don't want to sound clueless. I'm going to show you now how to pronounce at least some of the most important characters. This is all taken from this blog here. If you want to learn more about even more characters than we are going to look at, then you're welcome to click on that link, obviously. So let's look at a few of the most common symbols that we are going to use. Let's look at this one. How would you call it? And. Yes, and is a good idea. Ampersand might be even a better idea, because if you call it and, as you know, in C, when we use the logical and, we actually have to use double ampersand. And if you just say and, then maybe someone might think that you're already thinking of the double ampersand. So ampersand and are really common names. I will try to always use ampersand, which is the official name for that. Does anyone know a silly name for that symbol? A silly name. There are a few, according to this blog, and the one that I like as a German, of course, is pretzel. And that's because it looks a bit like a pretzel. But snowman and bow, this is also not too uncommon. What about this symbol? How would you call it? Star. Asterisk is good. Any other name? Multiply, yes, times. People often call it times. Times, star. I will probably most of the time call it star because it's shorter than asterisk. Any silly name that anyone knows? Let's see what the blog suggests. Splat, spider. Spider is nice. Twinkle, wild. Wildcard is quite interesting because this star symbol often serves as a wildcard in file names, for instance. If you say F star, then it means F plus anything. So it really acts as a wildcard. Okay, this symbol, how would you call it? Anyone? Double prime, quote. Yes, I think quote is a good idea. Double quote is what people also sometimes say. I will probably just call it quote. Now, I found rabbit ears, which is quite nice. Double prime, I'm not entirely sure why this was put under silliest name, except that it might be dangerous to actually call it double prime, because then it might be easily confused with prime. And we know that 2 primes is not the same as this symbol here. So I'm probably not going to call it double prime and just call it quote. Now, that's the character from the previous slide. Any clue how you would call it? Caret is the official name, yep. Not everyone might know it, though. So is there another word that, or another name that might be even easier to understand for someone who doesn't know the official linguist term for it? To the power, yes. Yep, you can say that. Although it often has more meaning than just to the power of. In some programming languages, it's also used for other purposes. Another good one, which is very common, is, so hat is quite common. Up arrow is also fairly common, although it doesn't really look like an up arrow, but it is often being used as an up arrow. Any silly name? Let's look at what is suggested here. Shark fin. It's quite nice, because it really looks a bit like a shark fin above the water. And fang, like a tooth. Makes a lot of sense as well. This symbol here, I think it's fairly clear. It's at, or at sign is the standard English name. Silly names, this is quite funny because this is probably the symbol that has the most silly names that you can think of. And here are just a few. Vortex, whirlpool, cyclone, strudel, snail and cabbage. It all makes sense. It looks a bit like a snail. It looks a bit like a cabbage. In many different languages, it has its own name. In German, for example, everyone would call it the equivalent of an animal called a spider monkey. And only because spider monkeys, they tend to look like this, a bit like, well, not really like the symbol, but every German would understand the German equivalent to spider monkey. Is there anyone who has a funny name from a non-English background and can translate it to English? Circle A in Chinese? Oh, that makes a lot of sense. It's an A with a circle. In Macedonia, it will also be just monkey, not spider monkey, but just monkey. Okay? Yeah, so I guess indeed every language, or many languages, have their own names. At and at symbol is clearly the easiest for us to use. This one, how would you call it? Exclamation mark, yes, I think that's fairly clear. Bang is very popular as well. If you hear a computer scientist say bang, then they prefer to say this because it's shorter than exclamation mark. Shriek, I'm not sure whether this is really popular. I probably will use exclamation mark. And this is variations of this bang, wow, or wham, or eureka. Eureka makes a lot of sense as well. Not, yes, not is a good idea as well. In many programming languages, this exclamation mark is indeed being used as not. And if you really call it not, and a non-computer scientist would hear you say not, then they would really question your sanity. But as a computer scientist, not makes a lot of sense. That's true. This symbol, hash. Yes, hash. Hash is what I will call it as well, sharp. I'm sure most of you have heard as well. Pound is quite interesting because this is American English. In America, everyone would call it the pound symbol. When I used to live in the States, whenever you call someone and they wanted on the phone, wanted you to press the hash symbol, they always told you to press the pound symbol. But this is really American English, and everywhere else hash is more common. There are some nice descriptive silly names, such as grid, fence. Octothorpe is good as well, because this is the official linguist name for that symbol, but almost no one, as far as I know, would really know this, so you shouldn't use it. Thud is one of my favorite English words, because it really sounds like a thud. Not everyone would understand it, though, and therefore grid might be understandable. The last one, how would you call that? Mod, modulo for yes. In most programming languages, this is being used for modulo division. And other than that, we can call it a percent sign, obviously. So I think we can use both. Let me put percent sign, but mod should be understood as well. And the nice thing about mod is that it's shorter. I found two very funny, silly names, which makes sense if you think about them. Grapes. It really looks like two grapes. And 007. 007 is nice as well. You've got double O's and then half of a 7 at least. So you could call it 007. All right, enough of that. One more slide that I've been asked to put on, and maybe you've seen that before. If not, then there is the student experience survey that may be waiting in your inbox. The sooner you complete it, the more chances you have to win. I'm not sure how that applies. But if you like, for example, this lecture, then tell everyone in particular through that survey that you do. Okay, now let's get into the actual contents of this week, namely data abstraction. And I would like to get everyone's attention back. Thank you. We will be talking about data abstraction. An abstract, well, first of all, a data type itself is a set of values. It can be atomic or it can be structured. A simple data type would be integers, and then integers is all the possible values an integer variable can take, all the integers. We can have structured data types, for example, integer stacks or integer queues. This is one part of a data type, and the second aspect to a data type is that we have operations on those values. If you have a data type integer stack, for example, standard operations that you should know from Comp 9021 is to push an element, to pop an element, or to ask the question whether the stack is currently empty. This is a data type. An abstract data type can be viewed as a logical description of how we view the data and operations without regard to how they will be implemented. That makes an abstract data type abstract. Abstraction creates what is known as encapsulation around the data, and therefore is a form of information hiding. This image shows what we mean when we talk about data abstraction. We have a data type that is somehow implemented, all the operations like pushing an element onto a stack, popping an element off a stack, etc., is implemented in a specific way. But from the outside, as a user of an abstract data type, all we see is the interface and the specification of these operations. But we don't see how it is implemented. We know what pushing and popping means as stack operations, but we don't care as a user when we talk about abstraction and encapsulation. We don't care about how things are implemented. Now, why is that so important for complex data structures? That is actually shown on the slide that comes after this one. Just to reiterate what I've showed in the image, the users of an abstract data type only see the interface, and someone who builds, who programs an ADT, then provides the implementation for everything that is mentioned in the interface. Now, the interface provides that user view of the data structure and therefore provides function signatures, which are also known as prototypes, for all the operations, such as pushing and popping. It sometimes provides the semantics of the operation via a documentation. Often documentation just means that when you provide the function interface, that you add comments as to how these functions should be used. And you can view all this as a contract between the abstract data type and its user or its client. The abstract data type developer promises that their implementation satisfies the logical or descriptive specification of these functions. The implementation itself then gives concrete definitions of the data structures and function implementations for all operations. Now, why is this important? Abstract data type interfaces are opaque. Clients cannot see the implementation via the interface. This is what is meant by encapsulation and information hiding. And this is really, really important as we start to develop more complex programs, because that allows us to decompose single aspects of these complex programs into individual parts or individual components. You definitely always should do that when you work in a team, but even when you write your own complex program, it makes a lot of sense to focus on specific aspects of your program at a time, make sure that these aspects are correctly implemented, and then forget about the details of this implementation to focus on other aspects. It also allows you to make implementation changes invisible to clients. If you have really separated your problem into individual implemented abstract data types and you feel the need to change the implementation of one of these data types, if you don't have to change the function signature, then you don't have to change anything else in your program. You really only work on the implementation of that one particular ADT, and everything else can stay the same. And that does improve not only readability of software, but also, most importantly, it allows you to structure your software into these individual components. When we have an abstract data type, and we will see lots of examples for this throughout this course, then typical operations with abstract data types will be to create a value of that type, to modify a variable of that type, or to combine two values of the type. Think of stacks of integers, for example. We might want to create an empty new stack of integers. We might want to push an element onto that stack that would be modifying one variable of the type. That doesn't happen too often that you combine two stacks with each other, but if you think of other more complex types like matrices, then you often combine two values of the type. You multiply two matrices with each other to obtain a third matrix. Now, common abstract data types, they consist of collections of items where each item might be a simple type or an abstract data type in itself, just like we have built up structures from simpler structures, our speeding ticket consisting of a simpler structure, date and time. You can nest abstract data types to more and more complex data types. And you often have that items have a key to identify them in that abstract data type. We will see examples of that later as well. Collections may be categorized by their structure. For instance, you might have a linear structure. An array is a very typical example of a linear structure. A linked list, which I hope you remember from Comp 9021 as well, is a linear structure. We will be looking at linked lists again next week. Branching structures, you can have trees, or you can have graphs, which then have a cyclic structure. And we will see examples of those later in this course. Usages of these structures could be an array, or a two-dimensional array could be used as a matrix. You can use an array or a linked list as a stack or a queue. You can represent a set. You can use trees for search trees, which we will do later, and you can use graphs for a variety of purposes, like a dictionary or a map, etc., etc. Just to illustrate what we could be looking at, we could be looking at linear structures like lists. This could be implemented as a doubly connected linked list. This is a typical example of a tree, and this is a typical example of a graph with individual nodes. Now, these individual nodes in a graph or in a tree, they themselves can be complex data structures in some cases, in which case we then would have hybrid structures where we may have an array, and every element in the array might be, as is illustrated here, a linked list. We will see exactly this as one way of representing graphs and all the information that you need about graphs. We will use an array of linked lists as a compact encoding of very large graphs later. For a given collection type, such as a graph, there are many different data representations possible. And for a given operation and data representation, also there might be several different algorithms that implement exactly the same operation. The efficiency of these different algorithms may vary widely, and not only widely, but also wildly. And we will see that generally, as we look at more complex data structures like graphs, there will be no overall best representation or best implementation of the data structure or the algorithm. And often what is the most efficient representation and the most efficient algorithm for operations depends on what you actually want to do with the graph later. The cost, therefore, depends on the mix of operations, such as how many inserts or searches you will have to do or how many deletions. And again, we will see examples later when we look at, in particular, graphs. What I want to distinguish for today's and next week's lecture, when we then look at dynamic data structures, is the difference between an abstract data object, abbreviated as ADO, and an abstract data type, ADT. I will make very clear what the difference between these two is. Just as a warning, Sedgwick's book doesn't really distinguish between ADOs and ADTs, and he calls everything ADT, although the first few examples, which I'm going to look at today here as well, they are actually abstract data objects. Objects, not types. And what that means will become clear very shortly. Let's look at one particular example. I will show you one abstract data type now, namely a stack, also known as a push-down stack or last in, first out data structure. And sorry, I'm just trying to, yep, all good. A stack, and I will in particular define a data object that is a stack of single character values. You hopefully remember from 9021 what a stack is and what the typical operations are. You can create an empty stack. Then you can insert elements into a stack, or as then they are typically called, you push elements onto a stack. And the stack then grows vertically. So you have an empty stack, you put an element on top of the stack, and then you put another element on top so that it grows. And you can also remove elements from the stack. And what would happen is you will always remove the element that was added last to the stack when you perform the so-called pop operation. So these are the standard operations: create, push, and pop. And it can also be important to check whether a stack is currently empty. This is a standard definition of a stack, and I hope that everyone remembers this from 9021. Here's a simple example. Suppose we start with no stack at all. We perform an operation create. Then creation itself is not a function that returns anything. It just creates the stack. We can, the stack would be empty after it has been created. We can ask the question, is that stack empty? Perform the operation is empty. The return value should be true because we haven't done anything with the stack just yet. Stack is still empty. Then I'm performing a push A operation. The character A is pushed onto the stack. That doesn't return anything, but it does change the stack. It's no longer empty. We have now the first element on top of the stack, which is A. Then I'm pushing B so that the stack will be AB. I'm pushing C, and the stack will then be ABC. This is shown sideways. Just view it vertically. You have A at the bottom, then B, then C, which is why when I then perform a pop operation, the element that was added last, C, is popped off the stack. The pop operation returns this character C, and AB is what remains on the stack. So if I ask whether the stack is empty, the answer should be false. So far, so clear, I hope. Just a quick question. If instead of a stack, I would have used a queue for these operations, where instead of pushing and popping, I would add elements and remove elements, which for a queue are always known as enqueuing and dequeuing. Which element would have been taken out first if I had performed the exact same operations? A, it would have been A, yes. So you have a queue from left to right. This is the last element that was added C, and the oldest element A then would be taken off if I had dequeued that element. Yes, that's exactly right. A is the answer to that question. And now let's have a look at how we can provide an implementation of a stack as a single abstract data object. And the objective now is to not implement a data type, which allows a client to generate as many stacks as the client wants, but we want to make it even simpler. We want to provide exactly one stack of characters. And this is what is known as an abstract data object. We want to design one single stack that a user can use, one object stack of characters. Now, the programming language C provides us with means to define the interface. And for the interface, we have to write what is known as a header file. They are always taking the extension H for header. And they define the interface that, when we think of information hiding or encapsulation, the client should see. That is, what functions do we want to provide for the stack data object that the user can use. And they are given here as so-called prototypes, where only the function signature, that is the return type and the parameter type, is being defined, and no implementation is given. So if you look at this, we have said that initializing a stack doesn't return anything, so the return type is void, and pushing an element doesn't return anything. Pushing an element should take an argument, namely which character is to be pushed onto the stack. And we have stack empty, which should return true or false, that is 0 or 1, depending on whether the stack is empty or not. And we have the pop operation, which is supposed to be take the top element of the stack. And therefore it returns, because we're talking about a stack of characters, it should return a single character. What this particular header file here also provides is that I'm going to create an implementation where I allow at most 10 elements on the stack. This, of course, is not very satisfactory, and a user that needs a larger stack couldn't possibly use that implementation. But before we look into how to extend this, we need to learn about dynamic data structures, and this will be deferred to next week. So for the time being, suppose that all I want to create is an abstract data object, a stack of a maximum capacity of 10. And this is given here with that symbolic constant as part of the header file. So this is what a client, a user of that abstract data object, can see. And we will see later how this is then being used in the programming language C, where a client can load this header file and then use these functions without knowing anything about the implementation. It's a bit like the header files that we have introduced already last week. Standard IO was a standard library, and remember that we've said include standard IO.header, which also meant that we could use all the functions that are defined in standard IO without us knowing anything about how they are implemented. And it's a good thing, because we don't want to know how these functions are implemented. What you see here is that there is, in that header file, no explicit reference to the stack object at all. So this doesn't provide an abstract data type, which would allow someone to define a stack by themselves. There's no type def in here, which provides the definition of a stack. And this makes it an abstract data object, not a type. The stack itself is really hidden in the implementation. So that's the interface, and now we can think of an implementation. The simplest possible implementation that I think we both can, or we all can come up with, is to use, because we have a fixed size, we say we don't want more than 10 elements in our stack, we can use a simple array of characters to represent this. And I will use an array of characters up to or of the size max items. And what I also need to know is where the current top of the stack is. The array itself wouldn't provide that information. So I'm also using an additional pointer that, or I shouldn't call it pointer, just an additional field in my data structure that says what is the current top of the stack. Which, if I've got these three elements on top of the stack, and I want to read it from left to right as before, then the top element would be 2. And this is all that I need when in order to implement this abstract data object. Now, the implementation is provided in a second file together with the header file that provides the signature and the interface to a potential client. There's an implementation in a file stack.c, which now contains real C code that implements, first of all, the abstract data object itself, and secondly, all the functions that I've promised to implement in the header file. Now let's have a look at this implementation. There is, first of all, the hash include stack.h. And do note the difference between including a standard library, for which we use this smaller than and greater than symbol. Since this is a program that I've written myself and is not a standard library which would have to be found elsewhere, what I have to use is quote stack.h quote. Make sure that you always use quotes when you include your own header file, and that you use these sort of brackets when you insert a standard library. Now, this implementation here inserts a standard library called assert, which provides basically one particular function that I will explain in a second as I go through this program. And then I'm defining my particular data structure. Just as I said previously, my stack should consist of an array of characters. Character items, I call them item, up to max items, and it contains an integer value to denote the top element. So it's exactly that structure that I've indicated here. We have the structure consisting of these two elements. That's my stack representation. And if you remember what I said last week, just defining this as a new type doesn't mean that we have an object of that type. For this purpose, I have to define a variable that takes this stack rep as its type. So I do define a variable which I call stack object of this type stack rep. And I'm using a new keyword called static, which has the effect, as I've repeated here, that when you use it within a file that provides a particular specific module to your program, that it declares this as local to stack, and all these functions are then able to use it. Whereas it's invisible from the outside. So this is my stack object, and with the help of that stack object, I can now implement all the functions that have been promised in the header file, in the contract with the client. First of all, to initialize the stack, all I'm doing is I don't care about the actual values in the array. They can be random values, but I do say that the top of the stack is -1. Remember that arrays always start at 0, so if I were to say top 0, then it would actually mean that there is already one element in the stack. But by saying -1, I clearly indicate that the stack is empty. And therefore, the function stack is empty can be implemented by saying I just return whether the stack object.top is smaller than 0, -1 in particular. Then the answer is true. Otherwise, I do have elements on the stack. The two remaining functions are pushing and popping. And with an array, it really is very easy to do this. If you want to push a character onto the stack, because we said we limit our stack to a size of 10, we have to make sure that we don't overwrite memory that doesn't really exist. And for this purpose, I have added a simple command here, which uses that assert procedure that is defined in that standard library assert. And I'm asserting a particular property that needs to be satisfied in order for the program to continue without failure. Namely, I'm asserting that the top element is smaller than max items minus 1. Max items was 10. If the top element is 9, then it means the stack is already full, and I can't possibly add any more elements to it. Now, this assert is the simplest possible way of dealing with exceptions, exception handling, in not a very nice way. What will happen is that if you have a test in assert and the test fails, then your program will terminate immediately. And the error message that you will get is that the assertion in this particular program at this particular point was not satisfied. This is all the output that you get. This is not very user-friendly. If you write a program for a user, then there should be a better way of handling these exceptions. It really looks like the unexpected error that you sometimes get, in particular under Windows, which doesn't explain anything, and which shouldn't really happen. But if you write a program just for yourself, then this assertion is all you need. Just a very simple way, as I said, to deal with errors. And it makes sure that the program does not continue, because if it were to continue, then it would access an element in the array which is not accessible. So given that I still have space on the stack, what I would do is I would say that the top of the element is now the top of the stack is now the next index. If my top was 3, then it is now 4. And I do add in element at array index number 4. I'm using an additional variable I that says take the top, and then at this index I add the character that should be pushed onto the stack. So I'm just taking the character that I get as an argument and put it on top. In order to remove an element from the top of the stack, I also use an assert, namely I make sure that there's at least one element on the stack. So the top must be at least 0, so that I have at least one element that I can take off. And what I can take off is the element that is currently at the index top. This will be the character that will be returned. So I'm taking it from the array, the top element. And I don't actually delete it from the array. There's no need to do this. I just reduce the index for the top element so that if, for example, I perform another push operation after this, the previous character will be overwritten. And I return the character. So that's how I could implement a single stack of characters. And just to remind you, this is exactly what is being defined here. The stack object is the variable that is accessible throughout this implementation here, which provides the object without this being visible to the client. The client has no idea that I've implemented this as an array, and that's a good thing because the client really is not interested in the actual details of the implementation. And what you would then normally do, if this was part of a larger project that you're programming, you would test this particular module thoroughly with lots of particular examples of pushes and pops and make sure that is empty works correctly. And once you've tested it thoroughly, you can leave that as is. Say, check mark, this part has been implemented, and then you can concentrate on everything else, in particular the clients that might want to use this stack. Let's look at one particular example where we use that stack, a very standard example to illustrate the usefulness of stacks is to use bracket matching. Is that something that you looked at in Comp 902.1 already? Okay, so let's just see how we could redo that in C and with the client that we have just implemented. So then you would have no problems answering the question, is the first expression of balancing means, just to repeat this, that every opening bracket, and in particular here we are looking at these round parentheses, square bracket, and these curly brackets have matching closing brackets. Is this expression correctly formatted? Is this balanced? Any problem with the parentheses here, with that first expression? No, all is good. So we only have this opening and the closing has a matching bracket. What about this one? Is not balanced because we have one parenthesis here at the end which does not have an opening, a corresponding opening parenthesis. And this is what we will call case 1 of an unbalanced expression. Is this expression balanced? Yes, it is. What about this one? No, it isn't, because here we have this opening and this closing, which doesn't correspond to the opening. A bit more interesting, what about this expression here? Is that correctly balanced? Any issue here? Yes, it is correctly balanced. Indeed, as it should. So a C compiler wouldn't complain about this because all the opening parentheses have corresponding closing parentheses. And this one here is obviously not balanced because there is an opening parenthesis which never has a closing counterpart. And this is what we will call case 3. So we have 3 cases. Here we have a closing parenthesis that doesn't have an opening. Here we have a mismatch, and here we have an opening parenthesis that doesn't have a closing parenthesis. So half the expressions, as we have seen, were balanced, and the other half was not balanced. Now let's have a look at the algorithm, which, given that you've looked at this in 902.1, you should already know, maybe not in precisely the syntax. The syntax here is again using this type of pseudocode that I will be using throughout this course to explain algorithms. And you can see what this algorithm does is it uses all the functions that our stack abstract data object provides us with. So that bracket matching algorithm takes as an input a sequence, or as we like to call them in computer science, a stream, S of characters, and outputs either true or false, depending on whether parentheses in S are balanced or not. Now what it does to use a stack is it takes each character in the sequence in the order in which they appear, and if it finds an open bracket, it pushes this open bracket on the stack. If it finds a closing bracket, then if there's nothing on the stack is empty, then this is like the first case that we had here. We have the stack is empty after we went through all these parentheses here, and then comes this closing parenthesis, which appears while the stack is empty, which means there's nothing corresponding as an open bracket. And this is why we call this case 1. The opening bracket is missing, and therefore we return false in this case. So we find a closing bracket, the stack is empty. That means not balanced. Else, we take the last element that was pushed, pop it off the stack, and check whether these are matching brackets. If we have a closing curly bracket, but the top of the element was an opening parenthesis, then this doesn't match, and this would be case 2. We can immediately return false. And we do that as long as we have characters in our stream, and when the stream ends, then if the stack is not empty, it means we still have one or more opening parentheses that didn't find a corresponding closing parenthesis, and therefore we would also return false. This would be case 3. Otherwise, we return true. Okay, very clear, I suppose, given that you have already seen this. Let's just look at an example when we have a very nicely formatted input that we see here. Then we can see how the stack evolves. At the beginning, we start with an empty stack. Then the first character we get is an opening parenthesis. It is pushed onto the stack. We get another opening parenthesis, also pushed on the stack. Third opening parenthesis, and now we have 3 on the stack. And what happens next is we first of all get this closing curly bracket. So we pop the last opening bracket and check whether it corresponds to what we just found. And indeed, this closes exactly this. And this happens with the next 2 characters also. The bracket corresponds to the closing bracket after we popped it off the stack, and what remains is this parenthesis. Then we find the closing, and first of all, the stack is empty because this is the last that is taken off the stack. We check whether the closing actually corresponds to the opening. And the next character here I'm calling EOF, end of file, the end of this stream. All is good. The stack is empty as it should be. If it was not empty, then there was still an opening bracket, but we don't have that here. And therefore, the answer of the algorithm will be everything is correctly balanced. Let's see what happens if we apply the algorithm to this input. And again, given that you've seen that already, it should be very easy for us to do this. Which is the first element that is pushed on the stack? If we go from left to right, it will be this, yes. So this is pushed on the stack. And again, I'm drawing the stack from left to right. What happens next is we have this. Will also be pushed. And this is our stack. Then we find this, which is a closing bracket. So this bracket will be popped off and disappears from the stack and will be matched against the closing bracket, which is perfectly fine. So the algorithm continues. We get to this point, and that means that we can also take this off the stack. Then we have this curly bracket. Does it look like a curly bracket? Not really. So that's our curly bracket. We have opening parentheses. We push it, we pop it, and match it against this. And then what happens? Do you see that this algorithm succeeds or fails at some point? So we've got this. This will be removed. Then we got another curly bracket, which is this one. And what is going to happen? So we've got these two. Push this, pop it again. All is good. Push, pop, push, pop. But here I've added this closing parenthesis, which when you then pop this off the stack, you see that this does not match this. And this is the point where the algorithm would return no. And it's exactly what a C compiler would do. It would find this parenthesis and would say this doesn't correspond to what it expects here. And in fact, compilers use exactly the same structure, namely a stack, to do this kind of bracket matching. So this summarizes everything that we have just said, the evolution of this stack. In this particular example, up to the point where we have these two curly brackets, we find the closing parentheses. The curly bracket is popped off the stack. The two brackets don't match, and therefore the answer will be false. Okay, so you have seen that also. Now let's have a look at how we can implement this in C by using the stack data object that we have already implemented. The first thing to do this is, if you want to use the stack, abstract data, I should actually have called it abstract data object because we really defined only one object. The first thing you have to do is, in order for your client to be able to use these stack operations, to hash include the header file, which means that you have access to all these functions without knowing how they are implemented. What we would also need is to handle the stream of characters as input. And for this, I'm going to show you as a quick sidetrack how we do that in C. This requires standard I/O, which we've already used last week, to print strings, characters, numbers. Now we look at how we can read numbers. There is two functions that I'm going to use. The first one is getting a character. That doesn't take any argument. It returns an integer, and it returns the character in the ASCII code read from the standard input, which usually is the keyboard, as an integer. Or it returns a particular symbolic constant, which is predefined, called EOF, end of file, which if you want to use the keyboard, you can simulate with the character sequence Control D on a Mac or under Unix, or Control Z on Windows, as I will do when I run this program to illustrate how this works. The other function that I'm going to use is to put character, which I've actually used last week already to put a single new line. I think was the example where I've added it instead of printing a whole string, you can print a single character. That writes the character to standard output, and actually it has a side effect, namely it returns the character that is written. Normally you can ignore it, but if you wish to test whether a character has been successfully written, then you can test whether it does return the character it should have written, or whether it returns EOF, end of file, on error. And with the help of this, we can now look at an implementation. Of all of this. So here we have the header file, which is exactly as I showed you earlier for the stack, with, in particular, the for function. Stack init is empty, push, and pop. Then here is the implementation, the stack.c. This is the file that we have here, stack.c. And it's exactly the implementation that we have seen on the slide. It defines stack object and then provides an implementation for these four functions. Let me close that as well. And let's have a look at the program that I wrote that implements the bracket matching algorithm. You can see in particular that I'm including the header file, but only the header file, not the implementation, to have access to all the stack functions. Then I'm defining, just to make it more readable, the three different types of opening parentheses and the three corresponding types of closing parentheses as symbolic constants. And then I'm implementing the three cases in just the main function that I have here. You see, first of all, I'm using the function provided by the data object to initialize the stack. Then I am reading the next character that is being input, that is being put in. And at the same time, I check whether I have reached the end of the input. And I continue this loop until I have found a mismatch. If I have found a mismatch, then I can terminate the loop because I know that the expression cannot be balanced. The first condition was if I find one of the opening parentheses, I push it onto the stack, and I do it with the help of the ADO provided stack push function. Else, if I find one of the closing brackets, I first of all make sure that the stack is not empty. If the stack is not empty, then I have one closing bracket too many for which I don't have a corresponding opening bracket. That means I can set the flag mismatch to 1. Else, I pop the top element of the stack and check whether the top element corresponds to the closing bracket that I've just found. So if it's of type A I think was the round parenthesis, then the closing must also be a round closing parenthesis, same for brackets and curly brackets. And if this is not the case, here I'm using the exclamation mark, the not, that is, it is not the case that either we have A or we have corresponding B or C, then this is the third case, the second case of a mismatch. And the last case of a mismatch or an unbalanced expression is when the stack is empty. So if I've encountered a mismatch, or I've reached the end of the file, but the stack is not empty, there's an opening parenthesis that doesn't have a counterpart, then I print unbalanced, else I print balanced. And this is now my program that in particular uses this abstract data object without caring about the implementation. It only uses the functions that have been defined in that module. And I think that is a very good time to have a short break. And after the break, let's continue 7:15. I will show you how we can now use a C compiler to bring it all together into one running program. Okay, time to continue. Everyone, take a seat. Part 2 is about to begin. Okay, a few quick, interesting questions I got during the break. As always, I would like everyone's full attention. Everyone, please stop talking. So one quick question was, can I combine some of these statements that I have here into a single one? Yes, you can do it. Instead of using that auxiliary I here, you could certainly put the stack object.top inside here. You could even combine that with the plus plus. So you could say stack object.top plus plus instead of the I, and then get rid of these two statements. I actually prefer the way it's written here, simply because it's more readable. Please stop talking while I'm talking, or just ask questions if you have any. Now, the reasons why I prefer this, as I said, it's more readable to divide it into individual statements. And every good compiler, you might think that it is more efficient to put it all, cram it all in one statement, but it isn't. Every good compiler would produce code that is identical in both cases. It would just combine these statements together. So just to make your life easier, try to make your programs as readable as you can. Second question is, I was hoping I didn't get it, but someone was smart enough to notice it. The get character and put character does have a bit of an unexpected signature, namely integer instead of char. This is just the way it's defined in standard in. You can use it as a char, and in fact, I have used it as char here. Instead of putting an integer here, I said put character char. And you can do that because C does what is known as automatic type conversion. So you don't have to worry about the fact that this is int, but the official signature is that this is an integer. All right, now let's have a look at how we manage abstract data objects and abstract data structures in C when we have these individual files that implement ADOs and later on ADTs, and we have clients that use these ADTs. How do we bring them together? Or if we have two different implementations for the same stack, for example, how do I know, or how does my system know which of the two I want to use? Now, this is then decided or done with the help of a compiler, just like the compiler that we've used last week, but now used in a more interesting way to compile different things together. Generally, compilers are programs that convert source code, like C, to executable form. Executable might mean machine code or byte code, just depending on what your compiler does and what your machine understands. We are using the GCC, the GNU C compiler, which first of all applies source-to-source transformation with the help of a preprocessor, such as replacing all symbolic constants that have been defined, like speed of light, by the actual number. And then it can be used in two different ways. It can compile source code to produce so-called object files. And it can then also be used to link object files and standard libraries to produce executables. Now, there are two different ways in which you can call this GCC for these two purposes. GCC with the command line argument -c means to compile, for example, C programs like list, main, and string into object files, which are called list.o, main.o, and string.o. Object files always have the extension O. And then you can use GCC with the command line option -o to link these object files. together with objects files for standard libraries, which have the standard extension .a, but you don't have to worry about those because they are provided by your system anyway, into an actual executable program, a.out would be the standard name, but of course we have seen that we can give it individual names. Now, if we want to use that with our example program, then what we would do is we would, first of all, compile our stack client, our stack ADO. With the help of -c, if we say gcc -c stack.c, it would produce the object file stack.o from the given stack.c and the header file. I can do the same thing with the C file that was the client of that abstract data object. And it would produce brackets.o from brackets.c and also from stack.h because it was included in brackets.c. And then I've got these two object files. This brackets.o does contain reference to some functions that are defined in the object file stack.o, like push and pop. It knows the signature, but it doesn't have any code for it. So I can't just run this brackets.o without linking it to the stack functions that have been compiled into this stack.o. And to do this, I can use the GCC with the -o option that then produces this file here, linking my object file brackets.o and stack.o. And here you see how, for example, if you have two different implementations, stack 1 and stack 2, if you want your bracket matching checker to use a particular implementation, you would have to tell the compiler which of these object files to use if you have two different to choose from. Libraries like standard I/O and assert standard libraries, they are automatically included. And fortunately, you don't have to say anything about this when you use the GCC function to link. So you can see that GCC is a multi-purpose tool. It can be used to compile, and it can be used to make executables. Before I'm going to show you how we can do that with our particular example program, let me mention that compilation is, as we write larger and larger programs consisting of more and more modules, a complex process. Now, a good thing is that we can get help from a system with the help of a so-called makefile, where we can tell the system what we want to have compiled for our particular project in such a way that ideally when we tell the system now compile an executable for my project, only things that have changed from last time will be compiled. Practically, if you have to do it manually, you should recompile everything just to be sure that you always use the latest version. But you can get help from the make command that is available under Linux and also on a Mac to assist you by allowing programmers to document dependencies in the code. And then it automatically does minimal recompilation just based on the dependencies that you have given. It checks how old the files are, and if the files haven't been changed since the last compilation, it wouldn't redo a compilation. So if we look at a program that consists of multiple modules, then this might be an example here. We can see here someone has implemented two different either abstract data objects or abstract data types or just modules. One is called world and the other one is called graphics. The graphics, as you can see, uses some functions in the module world, which is being included here. And here you can see main uses functions from both world and graphics. So you have some dependency. This graphics depends on world. This main depends on both world and graphics. And you can then use what is known as, or write what is known as a makefile, which makes these dependencies explicit, so that the system knows what to compile in order to produce a certain output. There is that Unix command make, which always uses what is known as a make file. And the make file specifies all the dependencies. And it also tells the system what needs to be done in order to produce a certain target output. The general syntax for a dependency is you give the target a name, which can be a.out, for example, or you give your program your own name, or it is an object file like graphics.o or world.o. And then you say what are the sources it depends on. Like on the previous, well, we have that here. The overall program, which I want to call game, depends on the three object files, main.o, graphics.o, and world.o. And what it should do as a command to build the target from these sources is it should call the GCC with the linking option to produce an executable game by linking these three things together. And if you put this all in a makefile, then you don't have to repeatedly type in this command yourself, but the system would just take care of that compilation by using that make program. And the general rule is that the compilation will only happen if the target itself, in this case the game program, is older than any of these sources, which means the sources have changed somehow because someone has made a change in one of the modules, and therefore these sources are younger than the executable, and if that is the case, then the compilation will be redone. So as a makefile for this particular example with the three modules, graphics, world, main, and the executable that we want to have in the end, a particular makefile, typical makefile that you would write would look like this. We would have the overall game program, which is obtained by linking the three object modules together. And as a example, let's look at the simplest, the world, which actually doesn't depend on anything. It only depends on world.c, unless it also includes world.h. If it didn't, then this is not necessary. So it depends only on world.c. And the program, or the way I'm calling the compiler here, to compile just this individual module would be GCC with the -c option. It will compile the world.c. And I'm adding a few parameters that I've already used in the previous lecture. -w all makes sure that it captures all possible warnings and errors. -w error even makes sure that every warning causes an actual error, so that I can't run this program, just to be on the safe side. And lastly, I'm telling the system that it should use the latest standard, namely the C11 standard, and compile under this. I recommend that you always use these three here, in particular for the assignments. I will ask you to make sure that your programs compile successfully under -w all, -w error, and under the C11 standard. Just to be very clear that when we run test cases with your assignments, that we all speak the same C dialect. So this is what is being done here to produce the module world.o. For graphics.o, it depends not only on graphics.c, but also if the header file has changed, not the implementation file. I don't care about the implementation file for world because it's an abstract data type or data object that is implemented in there. But the header file, if some of the function definitions have changed, then I have to recompile graphics. And I'm using the standard command to compile graphics. And same for main. I'm compiling main. And as you have seen, main is not only the main.c program, but it also hash includes the two modules, graphics.h and world.h. It also hash includes probably some of the standard libraries, but they are not supposed to be changing, so they don't have to be part of this makefile. Now, things to note, every target has to be in a new line and followed by a colon. This is just the syntax for these make files. And then followed by all the files that the target depends on. First rule for these make files, you always have one line like this. And the line that follows then is on, well, the new line, the next line, and must be indented with a tab character. So it is very important in order for a makefile to understand your syntax that this here is one single character, namely the tab character, and not 8 spaces. Then the system wouldn't be able to understand it. So that's how a makefile looks like. And now let's have a look at how we could write a makefile for our example program. Should remember my own password. So this is the brackets program. You can see it depends on stack.header. And I'm now going to write a makefile, just following the same structure as the makefile that we have seen here. So I could start with the overall program, which I think earlier I already called it RBT for random bracket tester, which will depend on brackets.o. This is the object file for the main program, this brackets.c, which I have here. And it will depend on the object file for my abstract data object, stack.o. And what the system should do, so I'm adding here the tab character. As I said, this is really very important. What should be done is gcc -o. It should just link the object files to produce the output RBT. So it would be brackets.o and stack.o, which are being linked. And this produces the overall program. Now, that needs two things, namely brackets.o, the object file for the main program. And it really is just like what we have seen on the example before. It depends on the C program, brackets.c, and on the stack.h, because the header file for the ADO is included. Again, a tab to say what it should do. It should do compile just my brackets.c with all the options that I like to have. The standard 11. And it should compile -c the program brackets.c. And lastly, stack.o. How should that be compiled? It should be compiled every time either the header or the implementation file have changed. And it is compiled with, let me just copy all of what I've got here. It should be compiled with the standard options and compile the stack.c. All right, so this is how we would set up the makefile. You can see that here, for example, I'm deciding here and here which implementation of the stack I'm using. If I have two different ones, then I would just use different files here. But the overall makefile makes very clear which I want to use. And we can now see here the stack header, the stack.c, and the brackets.c. Let's ignore this for the time being. I will use that a little later today. And the makefile that I've just written. Now, when I run the makefile, I can tell it to make a specific object, like stack.o. And it would execute the corresponding command. We told the system what to do to produce the executable for this abstract data object, and it has just performed that command. Now, if I don't change anything, and I run this make again, it would tell me there's nothing to do because it's already up to date. It's only if I change something, like in the header, which I thought was here. Why is that not here? It is here. If I change something, even if it's not very important, that change, it would realize that the file is new, and it would recompile it. This is one way to use it. The other way is I can directly go to make RBT, and then RBT would see that stack.o already has been produced, but it also requires brackets.o, and as you will see, it will do brackets.o as well. So if I just say make RBT, then it will perform all the compilations that are necessary. It will not recompile the stack.o because that was already current, but it will compile the brackets.c, and it will execute the link. And if I run this again, it will tell me everything is up to date. I can even just say make, and make means that it will always take the first target that it finds in the file, which is why it's always a good strategy to put the main program on top of the file, because then you just say make, and it will make your entire project. So that's what we have. It has produced a few files, such as stack.o. There are a few more files. This RBT in particular has been created, and I can now run this random bracket checker and just make sure that it works. End of file, as I said, is indicated by Control-D. If I put in Control-D, the input terminates, and the output is balanced. Whereas if I've got something like this, it says unbalanced. Any other example? I can actually run the random bracket checker on its own program to see whether the brackets.c itself is checked. I don't have to put it in. I can what is called a redirect. This will be explained later in a little more detail, but I can show you at this point the standard keyboard input to a file, and instead of typing something in, I can say take the input from a given file, and it would check brackets.c. The answer is yes. So the C program itself is balanced, as every good C program should be, although you should observe that the bracket checker did not take into account that brackets might also occur in strings. And if brackets occur in strings, then they don't have to be balanced. Of course, I can print a string that just contains one opening bracket, and there would be nothing wrong with that in a program. But in this case, it is perfectly balanced, as we can see. Okay, so this is how we combine things together. And as we have seen that if the make argument takes targets, then it builds just those targets. And if no argument, then it builds the first make file. In our particular example that we've seen, it was the RBT program. And here's the same thing with if nothing has been compiled before, it would perform all the compilations necessary to produce the target, which was called game. So write a makefile for the bracket matching program. Actually, we've just done that. Tick. And the last thing before I take another side step is to say that so far we have looked at abstract data objects where we have defined exactly one and only one stack, a single abstract object. We will then now also consider abstract data types, which are much more general in the sense that they allow clients to create and manipulate arbitrarily many data objects. So rather than providing just one particular stack, we will, when we talk about abstract data types, provide a type called stack, and then someone could use as many stacks as they want based on that ADTs. The idea, however, is the same. Everything will be encapsulated. That is, the abstract data type will again not reveal the implementation to a client. Now, before we can do that, in C, these abstract data types are implemented using what is known as pointers and dynamic memory allocation. And this is what will occupy us now for the rest of today, namely pointers, and next week, namely dynamic data structures. So let's have a look at pointers. Before I can talk about pointers, I have to talk about computer memory. And in order to talk about computer memory, I have to quickly talk about numeral systems, assuming that you also all know this from Comp 9021. A numeral system is a system for representing numbers using, well, normally digits, but sometimes other symbols. In particular, if we don't have enough digits, then we have to use other symbols. Most cultures, as I'm sure you know, have developed a decimal system based on 10, although there exist cultures that have tried other bases. Whereas for computers, it is much more convenient to use binary numbers where the base is 2, or for readability purposes, hexadecimal systems where the base is 16. As you know, the decimal system uses the base 10, and for this purpose we have exactly 10 digits from 0 to 9, so that when we read a string of digits like 4705 as a decimal number, then of course we know what it means, namely 4,000, 700, 0, 10, and 5. And this is easily computed with regard to the base 10, where the place values tell us what the actual 4 at this position means, namely 4 times 10 to the power of 3. So obviously this is 4,705 in a decimal system, whereas if we look at a binary system, then the base is 2, and obviously we have only 2 digits, 0 and 1. In which case we would read a string like this, not as 1,101, but rather as 1 times 8, 2 to the power of 3, plus 1 times 4, plus a 0 here, plus 1, with a similar structure for the place values. And if you compute this as a decimal number, we obtain obviously 8 plus 4 plus 1, which is 13. Now, we will write this as this string here to make clear that we talk about binary numbers. 0b is the standard way in which these numbers are indicated in C. So instead of writing x equals 13 in a C program, you can also write x equals 0b 1101. That would have the exact same effect. Now, since binary numbers are sometimes hard to read because you get long strings of bits, a hexadecimal representation is very often used when we talk about computer memory and specific bytes in our computer memory. Any questions? I'm assuming that I'm repeating material from 9021. Yes, good. So this is why I'm going through this fairly quickly. For the hexadecimal representation, the base is 16, and since we don't have 16 digits, the standard is to use the standard 10 digits 0 to 9, and capital letters A to F. And when we then see a string like 3AF1, which uses the digits available for hexadecimal numbers, this would be interpreted just as usual, but now to the base of 16, so that the first 3 here would be multiplied by 16 to the power of 3, plus 10 times 16 to the power of 2. F is 15, so we have 15 times 16, and the 1 will just be taken as a 1. So that this number, if you compute this as a decimal number, corresponds to 15,089. If you can't see that immediately, just believe me that this is correct. And in C, we would denote hexadecimal numbers with the prefix 0x. So just like before in a C program, instead of writing 15,089, you can also say 0x3AF1. And since you all know this, it would be very easy for you to tell me what 74 as base 2 would be. Anyone? 64 plus 10, yes. So you've got 1 for 64, and then, yes, so 1 for 64, then 0, 32, 0 for 16, and then 1 for 8, 0 for 4, 1 for 2, and 0 for 1. Yes, very good. What is hexadecimal 2D in decimal? $45, that's correct. 32, 2 times 16, plus 13, D is 13. Then when you see a string like this, it will be hard to convert to base 16 just by looking at the string, but if you color it into 4-bit chunks, it is actually very easy. And this is why conversion between binary and hexadecimal is much easier than using decimal. Obviously, 1, 0, 1, 1 corresponds to 11, which is B. Then what's 1, 1, 1, 0 is D. And this is just 2. And this is 9. All right. And in the same way, we can translate 1, 2, and D to base 2, just digit by digit. This would be just 1. Then the 2 would be 0, 0, 1, 0. And the D just being 1, 1, 0, and 1. Not 1, 1, 1, 0. That would be E. And 1, 1, 1, 1 would be F. But the reason why I'm showing this is because we have to talk a little bit about computer memory before we can talk about pointers, before we can talk about abstract data types implemented using dynamic memory allocation or dynamic data structures. Computer memory is large arrays of consecutive data cells or bytes. We know, and I think I've mentioned that last week, that a character always takes 1 byte of memory. An int and a float, at least on a standard CSE lab computer, takes 4 bytes, and a double precision floating point number takes 8 bytes. When you declare a variable, like you say int x or double y, the operating system finds a place in memory to store the appropriate number of bytes. So it will reserve 8 bytes when you declare a variable as double. And what then actually happens if you declare a variable called k, it finds the corresponding number of bytes, and you can, in C, access the address in the computer memory with the help of that ampersand symbol. So you can take your variable k, which has been defined as, let's say, double k, then the starting address for these 8 bytes would be accessible by that syntax ampersand k. And this is also known as the address of that variable k. Now, it is convenient and standard to print memory addresses in hexadecimal notation. We will do that as well, and the advantage will become clear as we go through this course. What is also standard is when we display memory that low addresses are shown at the bottom and higher addresses on the top. So if we have a computer memory that for which we only need 4 hexadecimal digits, then any of these bytes could be the starting, if all that memory is free, the starting address of our particular variable k. You can actually do this and test this with your own C program and system. You can declare 2 variables, k and m. Here they are declared as integer variables. And you can print the address of these 2 variables. For this, you would use the placeholder %sign p. Why p? P is being used because this is also known as a pointer. The address of a variable can be accessed through a pointer. And then you can output the address of k by variable k by accessing it with the help of that ampersand symbol. And then the output that you can get, of course, that depends on where and when and how you run this program, on which computer. It is very unlikely that you will get exactly that output that is shown here, but you will get 2 addresses at the start as the starting point for these 2 variables. And it is very, very likely that you get 2 consecutive starting addresses simply because they have been defined consecutively here. But it is not guaranteed. It could be that your processor and memory is shared by another process that is running at the same time and is also using memory, and therefore you can't rely on the fact that these are just 4 bytes apart. What you can be sure of, however, is that k occupies the 4 bytes from the starting address, which would be 80, the first byte, 81, the second byte, 82, the third, and 83, the fourth byte. Remember, integers take 4 bytes, and same with m. Similarly, when you declare an array, the elements of the array are guaranteed to be stored in consecutive memory locations. So if we declare an integer consisting of an array consisting of 5 integers, then we can access the starting address of every individual element with the help of that usual ampersand notation. We can output it, and you will see that no matter what the first number is, this is really random what you get, but the next numbers will always come in 4-byte chunks. This is where then the 5 elements of that array will appear. If you had a character array of 5, then the difference would, of course, be only 1 byte. And if you have a double precision number, then the difference would be 8 bytes instead of the 4 that we can see here. Where can we use this address? There is one standard function where you actually have to use the address of a variable, and that is if you don't want to use getChar, which only gives you 1 character at a time, but you want to read more complex input, such as numbers, then the standard I/O function to do this is called scan scanf, which corresponds to printf. Instead of printing, it scans the input. And this function requires the address of a variable as an argument, so that it knows where to put whatever it reads as a number to. Scanf can use a format string just like printf, so you can even read several numbers at the same time. You can use, for instance, just like you print a number, an integer with the help of the %d placeholder. You can use this to read a variable. Then as an argument for scanf, you have to provide the address of, as I said, the variable where the input should be read into. So in order to use this function, simple example, you want to ask a user to input an answer, an integer as an answer. Then you can print a string, enter your answer, and then the system would halt when it sees the scanf command and wait for the user to input on the keyboard. Would be the standard input, a number that will then be, or just some input that will then be interpreted as an integer according to that $d placeholder. And the result will be put at the address of a variable that you're giving here. If you want to read a floating point number, a standard 4-byte number, you would use the placeholder %f, and then whatever scanf gets as input will be interpreted as a floating point number and will be put at the address of a variable that has been defined as a floating point number. If you have defined a double precision floating point number, you would use the %lf sign and also put the address of a variable that then in itself has been defined as a double variable. So this is scanf, and as we see, it uses the ampersand syntax to provide the argument where to put whatever is being read from the input. What doesn't become clear from that simple use of scanf, but can be very important, is that scanf returns a value, namely the number of items read. And this can be used to determine if scanf has successfully read what you were asking for. In particular, if you're asking for a number, then the user could input a string like ABC, and this cannot be interpreted as an integer. And what would then happen is that scanf doesn't assign anything to this address, but it would return 0 as the number of successfully read numbers. And in this way, you can check whether you really got a valid input or not. This can be very useful. And as a simple exercise, I wanted to look at a program that asks the user for a number using exactly this structure, checks whether a correct number has been entered and whether this number is positive, and then apply a process that you should have seen if you've done the homework for last week, a process that is taking a number and rewriting it, replacing it by another number depending on whether the number is odd or even until 1 is reached, which is also known as Collat's process, named after the mathematician who invented this. So let's do that before we have our second break, in order to see how we can use scanf to scan for input. Here is the first part of that program, which I've just copied from the solution to the homework last week, which defines that function Collat's that takes an integer as an argument and then replaces this by either dividing it by 2 if it's even, or multiplying it by 3 if it's odd, and adding 1 until 1 is reached. And Collins's conjecture is that whatever the input is, eventually, after finitely many steps, there will never be a loop. You will always reach 1. This, however, is not the point. What we want to do is we want to ask the user for input. And for this purpose, we would define our main function. We don't need arguments for it. It will be helpful to have a number n into which we want to read the input. And then we want to ask the user for input. So just like in our example that we had on the previous slide, we would enter something like, please, or we ask the user, please enter a number. You might even be wanting to indicate what you actually want, a positive number. So that this is being printed. And then we want to use scanf to read a number. And at the same time, we want to check whether the number has been successfully read, whether the user didn't input a string, and also whether the number is greater than 0. Now, we can do that in one go by putting the scanf into a condition. We want to read an integer. And we want to add this integer to the address of the variable n, which we have defined for just this purpose. And it's a good idea to check whether we actually got a number, which we can do by saying that this must be 1. One number has been successfully read. If this is 0, it would mean that the user, for example, has input a string ABC instead of a proper number. This is one thing that I wanted to check. The other thing that I wanted to check is the number is really positive, because the user could enter -1, and we are only looking for a positive number, and I can do this as part of this scan as well. Check whether it really is greater than 0. And only if both conditions are satisfied, then I want to apply the function that I've defined above. I think that's it. What you could do, if you want to make it more user-friendly, is to add an else condition that says that if the input is not a positive number, it's either a string or a negative number or 0, then you could output that as just a comment why the program doesn't produce anything. But this is not really required here, so I'm just using return 0 and close the main program. So that shows how we can read input. Now let me see whether I've really programmed that correctly. Well, I'm not going to input everything, although I normally should do this. That was called collats.c. It does compile. It would have produced an executable a.out. I think it's what just appeared here. Yep. So I can run this. It asks for a positive number 10. And indeed, it applies this process of dividing the number by 2 if it's even, and multiplying by 3 and adding 1 if it's odd, until I obtain 1. And we can see what happens if I enter -1. Then the number is successfully read, but it's not greater than 0. So the system doesn't do anything, or the program doesn't do anything. And if I enter just nonsense, then the scanf would return 0, because 0 numbers have been successfully read. And again, it doesn't do anything. So that's the first simple application of the use of the ampersand symbol. Scanf requires this as an argument. And that's a good time to have another short, let's say, 5-minute break before we start with the last part, where we go deeper into using addresses and pointers. Okay. Yeah, last 40 minutes for tonight. Here's the same program that I have just written. One question I got during the break was, can the scanf return a number different from 0 and 1? Not in this case, but what you can do is just like in the printf case, you can put 2 or more placeholders in here, and then you would have to add another variable here. So you could read %d and then another %d with a space in between, and then you can add another variable %m. And then the system would return 0. If no number is correctly read, it would return 1. If one number is correctly read, but not the other number, and it would return 2 if both numbers have been correctly read. So that was one use of the ampersand. And now let's finally have a look at what is known as pointers. In C, but not only in C, in many other programming languages that use explicit references of computer memory addresses. A pointer is a special type of variable which stores the address that is the memory location of another variable. A pointer itself occupies space in memory just like any other variable of a certain type. It would just be a variable of the specific type pointer. The number of memory cells that are needed for a pointer, that actually also depends on the computer's architecture. If you look at very old computers or very simple handheld devices that have only 64K bit of addressable memory, then you would only need 2 memory cells. That is 16 bits to hold any address from 000 to FFFF. So you would only need 2 bytes. For a desktop machine that has up to 4 gigabit of addressable memory, you need 4 memory cells. 4 memory cells, 4 times 8 bits is 32 bits, and that can hold any address starting from these hexadecimal 8 zeros to 8 Fs. And this is corresponds to the number 4 gigabit. This is what a desktop machine normally has, and our CSE lab computers have that as well. Whereas modern computers, and they are called 64-bit computers, are called 64-bit computers because memory is addressed with 8 bytes, which in principle means that you can address 2 to the power of 64 bytes, but this is far too much than what you would normally have in a computer like this. So this is a 64-bit computer, and if you ever wondered where that name comes from, 32-bit and 64-bit, this is exactly what it is. It defines the range of addressable memory. In practice, the amount of memory for 64-bit computers is always limited by the CPU. But it means that when I write a C program for this computer and I declare a variable as a pointer, every such variable will occupy 8 bytes, whereas on a CSE lab computer, and this should be our standard reference, it will occupy 4 bytes. Yes? Not at all, not necessarily. It really depends on what type of variable you're declaring. There are different regions in your memory, and we will talk about this in much more detail next week. Typically, you start with lower address, but you have different areas for different purposes, and it does not necessarily mean that you reach the limit. So now, what do we do with pointers? First of all, how can we illustrate this? And I really very highly recommend it to always do this when you deal with pointers, to draw a little diagram. which illustrates what actually happens, because then it's so much easier to see and understand what an algorithm with pointers does. And it's also so much easier with a little diagram to understand what you have to program in order to properly use pointers for your problem at hand. Now, suppose that you have a pointer p that points to a variable of type character. Assuming that the pointer p requires 2 bytes, which is, of course, not true for most computers, but just assume that this is the case, to store the address of the variable c, here's what memory, the memory might look like. Suppose you have said that this pointer variable should get the value as its value, the address of the character variable c. Then the character variable itself would occupy 1 byte, and the pointer variable would occupy 2 bytes, and this pointer variable would point to this memory cell here. Of course, you don't really have a pointer like an arrow like this. What you do have is, if this has a specific address, let's say hexadecimal 12AB, then in here you would have the value 12AB. But it's a very nice way to draw an arc like this to just depict the fact that this now has the address of this variable here. Now that you have assigned to p the address of, in this case, variable c, you may want to be able to reference the data in the memory location of that address. And for this, we use the star symbol, or the asterisk, to access the object the pointer points to. So, for example, if you want to change the value of that variable c using the pointer p, you can do that by saying that star p gets the value character t. And what the system then does is it's looking at the address where p points to, and at this address it inserts that character t. Now this is sometimes described as dereferencing the pointer, and that makes sense because you have the address as a reference and you dereference to the location where this address or where this pointer points to.
Sorry, does that change it to character T or to the reference of character T?
No, it changes it to the actual character T. So what happens if you see star P? It will look at what the address here is. Say it's hexadecimal 12AB. And then at this address here, it will replace the contents by that character T. So it will overwrite anything that is in here by the character T. Things to note at this point is that all pointers are constrained to point to a particular type of object. So here, when we define S as a pointer, just like we use the pointer P, we also have to say what type of pointer we want. Therefore, we would say character pointer S to declare S as a variable of the type pointer to a character. And here we declare P as a variable of type pointer to an integer. Yes? Yes, yes. We will not do that right now, but we will do that a little later. You can have, if you look at this memory, you can have another pointer here that points to this address. And actually, this will be important as well. It will start to look a bit funny if you have this pointer and you want to indirectly address this variable. You will have to write star star this pointer because you have to dereference the pointer that is being the result of dereferencing the other pointer. And you can do that as long as you like. You can have triple stars and quadruple stars. I have never seen triple stars, but double stars, this is really very common, as we will see later. If then you have a pointer that has been declared as an integer pointer, then and it points to an integer variable x, it really does make no difference to saying that x equals 3 or to say star p equals 3. The effect would be the same. The contents of this variable x, where p points to, would be changed to 3. So let's look at an example where we do this, and it is actually going to help to draw a little diagram to understand exactly what is going on here. Now, first of all, we are declaring p as well as q as integer pointers. And one thing that might be a little confusing if you see that for the first time is just the syntax that is being, nope, that's not what I wanted, document camera. The syntax that is commonly used for declaring pointers. I should switch it on. As you can see on that slide 56, integer star p declares p as I've got it, as a pointer to an integer. The way this should be read is we are declaring a variable of type integer pointer. So we are declaring p as pointer to an integer. Now you can write it in this way, but it's very common in C programs to omit these parentheses and to just instead write integer star p. But it should be very clear that this star symbol is not dereferencing anything at this point. It just means really this. I declare p to be of this type integer pointer. So that's the first thing. Then if you go back to slide 56, what you see is we also define an array, integer array, 5 elements, and we have 2 standard integer variables, x equals 10, and another integer variable, y. Now, how would that look like in memory? We would have the variable x, which has been initialized as 10. We have y, which hasn't been initialized as anything. And then we have our array A, and we have the 2 pointers P and Q. Now, the first thing that happens in this program is that P is assigned the address of X. So somewhere we have our pointer P, which occupies on a standard CSE computer 4 bytes. And it doesn't point to anything at the beginning because it hasn't been initialized. But after that first command, P equals %x, it means that P now points to X. So that when you then say star P equals 20, it means that we are dereferencing the address of P, which is this memory cell here. And star P equals 20 will have the effect that this value is replaced by 20. So if you now ask what is the value of X at this point, it has changed through that, indirectly changed through that star P equals 20. When we then say y equals star P, what would be the effect? It means that y does get the value of wherever P points to. And P points to 20. So that y equals star P has the effect that y now also gets the value 20. So you see how you have to read very carefully what's going to happen here. You could also have said y equals x. This would have had exactly the same effect. Y equals star P also means that y now has the value 20. And then what also happens is we have our array A, which is 5 times 4 bytes long. Why 4? Because every integer takes 4 bytes. This would be array 0, array 1, array 2. So when we then say P equals the address of array 2, P would now point to this address here. Or to be precise, it would actually point to the very beginning of that 4-byte element. And lastly, when we then say Q, Q hasn't been used at all. But if we say Q gets the exact same address as P, the effect would be that Q now also points to exactly that address. So this is how we can declare pointers and how we can use pointers and addresses. Let's have a look at this program here and look at it carefully to see what it will do. And I wonder if anyone could tell me what the actual output is going to be at the end of this program. Just go through this program step by step to understand how things are being assigned, and then maybe one of you is able to tell me what the result is. Yep, I think I heard the right number. Let's give everyone else a chance. I admit it's actually hard to do it without pen and paper, so it might be a good idea to actually use pen and paper to just follow what happens. 90 is not exactly correct, but sounds like, yes, 120. That's correct. And I think I heard it before, so 120 is the actual result. Now, to give everyone a chance to see how we actually arrive at that 120, let's just draw a diagram that illustrates what is going to happen here. We start with two integer variables, I and j, and their initial value is, so they are somewhere, and their initial value is 10 and 20. And then we have two pointers, pointer 1 and pointer 2, which at the beginning get the address of I and j respectively. So this is what happens in line 7 and 8. Then in line 10, we say that the contents of the integer where pointer 1 points to is replaced by the contents of where pointer 1 points to plus the contents of where pointer 2 points to. So we dereference pointer 1, get 10. We dereference pointer 2, get 20. And if we sum this, then the result is 30. And this will be the new value for star pointer 1. Star pointer 1 is this address here. So we do get 30. This is line 10. Line 11 now redirects pointer 2 to wherever pointer 1 points to. So it is redirected up here. And we no longer have this. And then we see that now whatever pointer 2 points to, which actually happens to be the same that pointer 1 points to, is twice the value of pointer 2. And therefore, this is multiplied by 2, which is replaced by 60, because this is what in line 12 we assign to the memory cell that pointer 2 points to. And now I think that what could be a possible reason to come up with 90, if you were to sum these two, that would actually be 80. But if you had replaced, if we didn't have the pointer 2 equals pointer 1, then we might have had 60 in here, and then 60 plus 30 would give 90. But this is not actually what happens. What happens is now at the end, we output the contents of where pointer 1 points to plus the contents of where pointer 2 points to, which is actually the same in both cases. That is, we output 60 plus 60, which is 120. And you can see that just by drawing a little diagram like this, it becomes very easy to understand exactly what happens. So again, my recommendation when you deal with pointers, and we will have to do that a little bit over the next 2 or 3, well, 2 lectures in particular, then draw diagrams. That always is very helpful. $120 indeed. What are possible applications of pointers? Here's a very nice and very simple one that illustrates the use of addresses if you want to perform certain operations on variables directly. Question is, can you write a function to swap 2 variables? So you've got a main function somewhere, you have 2 variables a and b, and you want to write a function that swaps the 2 values that a and b currently have. Now, if we were to do it without pointers, then we might attempt to do it in this way. Swap integer a and b. We say a temp variable gets the value of a then gets the value of b, and b gets the value of temp. The problem is, if you try to do that, then because in C, parameters work as call by values. If it's not arrays, we have seen arrays are slightly different, but if it's variables of standard type like integer, and you have a is 5 and b is 7, and you call swap, then you will see that in the end, a is still 5 and b is still 7. And why is that? Because all the function takes here is the 5 as an input and the 7 as an input. So it gets the 5 and it gets the 7, and it swaps these values around. But this doesn't have any effect on these numbers, on these variables a and b here, because it's only the numbers that are being passed as arguments.
Does that mean we now have 2 locations in memory for that value?
Yes, you actually do have them at this point when this function is being called, because here you have the variables a and b for this main function. Here you have these variables a and b that are local to the swap function, which are 2 different variables. And memory cells are being created for these variables. But when the function terminates, this will be freed again. So it will, these 2, and in fact these 3 variables will be thrown away. So that if other functions are being called, this memory can be reused. So you've done that swap here with these copies of the variables, but all the information is lost and has no effect on these 2 variables. Yes, that's exactly right. But we can do this if we take into account that we can use addresses, and we can pass on addresses of variables as parameters. We've seen that the call by value means that changes made to the value of a parameter do not affect the original. And function swap was indeed trying to swap the values of the original real variables a and b, but because it used a copy of these variables, it didn't achieve anything. Now we can achieve this by simulating call by reference, where instead of passing on the values, we pass on the address of the variables where we want to make the swap. And we can do that now with the help of pointers, which then allows the function to change the actual value of the variables. So to do it in the right way, we would do it like this. We would have our variables a and b here, and instead of just passing on the numbers 5 and 7, with which the function can't really do anything, we pass the addresses of the 2 values. And if we do pass addresses in memory, then what we do have here as parameters is pointers, integer pointers. We get two addresses, one for the variable A and one for the variable B. And if we now say that we copy the contents of the address that we got for the first variable into our temp, and then we copy the contents of the second address into the memory cell where the first pointer points to, and into the memory cell where the second pointer points to, we then copy the value that we have temporarily stored. The operation will now, or the function will now operate on the actual memory cells for A and B. So if you then run this program, you will see that A and B have successfully swapped values, because the change will have happened at the address where these two pointers point to. And therefore, whenever you want some variables to actually be changed, you have to pass on the addresses as parameters to a function. You may remember that when we sorted the array last week, without me going into detail, it actually did work. And the reason why it worked is whenever you have an array as an argument, what C actually does is pass a pointer to the start of the array. So it actually has the exact effect that we have here as well. And this has to do with the way arrays are being treated when they are arguments of functions. This is what I will talk about next. When you have arrays, there is actually two equivalent ways of iterating through these arrays and accessing the individual elements of these arrays. Now, instead of using a for loop that uses the index, the standard index for I equals 0 to I smaller than maximum, another possibility is to determine the address of the first element of the array, to determine the address of the last element of the array, and then use a pointer that scans through the array. And what that requires is the use of so-called pointer arithmetic that allows you to very easily move from element to element. And you would terminate the loop when the address exceeds the address of the last element. So to give you an example, suppose we have an integer array of size 6. Then we can iterate through that array by using not an index variable, but a pointer variable that starts with the address of the first element, ampersand A0. And then while the address is not larger than the address of the last element, we can do this because we know an array will always be in one linear chunk of memory. While we have not exceeded the address of the last element, we can access an individual element of the array by just saying star p. And star p at the beginning will be the contents of the address of A0. In other words, it will just be A0. And then when we increment the pointer, it will jump to the next element. So we take the current address, we increment that address, and that will point to the next element. Will it really? Because if you add just 1 to the address of a pointer, will it really point to the next integers? We have learned that an integer takes 4 bytes. How does that work? The secret is actually in that pointer arithmetic. And I will show you how that works, not on this slide, but on the slide after. Just to give you a clearer picture of what happens in this piece of program. You have the address of the first element, and this is now the same the same type of loop, but not written as while loop, but as a for loop, which is probably the more typical way of writing this, where you start at the address of the first element, you continue until you've exceeded the address of the last element. And you could either say smaller or equal to at A5, or really smaller than at A6, which doesn't really exist. And you increment the pointer, which allows you to move to the next element with the help of what is known as pointer arithmetic, as I will show you on the next slide. And then inside of the loop, you would access the current array element with the help of dereferencing the pointer. Because of pointer array connection, you can always, when you refer to an array with an index, replace this by dereferencing the address of the array, which would be the address of the beginning of the first element, plus the offset I, which would be 0 if you talk about the first element at 0, or a larger number if you go to the second element, third element, and fourth element. But now why A plus I? And that has to do with the fact that C, as well as many other programming languages, use pointer arithmetic. Remember that the pointer variable holds a value which is an address. And remember also that we said when we declare a pointer, we have to say what type it points to. We make a distinction between an integer pointer and a character pointer. And because we do this, C does know what type of object is being pointed to. Therefore, in particular, C knows the size of that object. It knows that a character takes 1 byte, and it knows that an integer takes 4 bytes. Therefore, C can compute where the next or the previous object is located. And if you tell C then to advance the pointer by saying pointer plus 1, it will actually jump 4 bytes ahead if it's an integer. And it will jump 8 bytes ahead if it's a double precision floating point number. It will only advance by 1 byte if it's a character. So if we have a declaration like the array with 6 elements, and suppose this starts at address hexadecimal 1000, you define an integer pointer, P, and set it to the address of the first element. Then P now has the value 1000. And if you then add just 1 to P, it doesn't have the effect that the resulting address is 1001. It means the resulting address is 1004, where the next integer would be found. And this then makes it possible to do a loop like this, where when you say P plus plus, it will actually mean P plus 4 bytes in case P is a pointer to an integer. Question?
Yeah, I can explain.
Yep.
When you're saying B equal ampersand A bracket 0, could you just have written just B equal ampersand A? Because you say A is a pointer to the first element, right?
As a matter of fact, no, but what you could have said is P equals A. So A itself, the symbol A corresponds to the address of the beginning of the array. So instead of saying ampersand A0, you could say P equals A. But this is much more readable. I prefer this because it makes very clear what I'm trying to access. So generally speaking, pointer arithmetic means that when you declare a pointer as pointing to a type T, and your pointer initially contains an address A, and you execute the command advance P by K, then it will change the value of P to the address A plus K times the size of the type T. So if you have an integer pointer and you say P equals P plus 2, it will advance 8 bytes because 2 integers. The value of K can be positive or negative. So if you say P equals P minus 2, it will jump 2 bytes back. two integers back. That is 8 bytes in case we have an integer pointer. So again, if we look at this, and we now say when we declare the pointer, it has an unknown value. We set it to the start of the array, which was this address here. If we now say p equals p plus 2, it will point to 1008, 2 integers ahead. This is a different if we have character arrays and character pointers. The system knows that a character takes only 1 byte. So if our character array, our string as we might call it, starts at address 2000, and we set q to the beginning of that array, we now say q equals q plus 1, or increment q, then it will jump only 1 byte ahead, because we know it's a character pointer. This is very, very useful when we use these pointers to iterate through any structure, in particular an array, because we don't have to worry about how many bytes exactly we have to jump ahead. The system will do it automatically. And this is particularly important if you want to write portable code, or to ensure that code is portable. If I write a loop on this computer where it has to jump ahead 8 bytes for an integer, then I use the same C code on a lab machine where it has to jump ahead only 4 bytes for an integer. It will work automatically, and I don't have to rewrite the program.
After you quantity the first element of array A,
Mm-hmm.
is there any possible way that you can quantity to the second element?
Yes, you can do that. Well, I'm not even sure exactly what would happen. It's probably not a good idea. There are 2 things that might happen. The first one, you can certainly, no, actually you can't, because how would you know? So I have the value here, and I know the exact address, but how would you know it? So you can't just write p equals p plus 2. What you could do is you could copy that address into a character pointer, then advance the character pointer by 2, and then copy it back into p. But what will happen then is probably chaos, because it's not very clear what the system will do, whether it will automatically advance p to the next one because it's an illegal address, or whether it will interpret the last 2 bytes of your integers and the first 2 bytes of the next integer as one integer. Yes, the compiler knows this, but what the compiler doesn't know is what you can certainly do, and again, I don't really recommend it, but you can define an integer pointer p here, and then you can initialize it with an address of your choice. You can just say p equals 500,037,666, maybe hexadecimal if you want. And then you give it a value, and this value will be copied into that address. And you might want to read what you find in this address, but you really don't want to write into that address because you really don't know what it points to. Your system will not allow it. If you try to address memory which is being used by the operating system, then it will just not allow you to put anything in. It will just end with a runtime error, which would say that, oh, you're trying to write into memory that you shouldn't really access. But in principle, you can do it. You can assign any address to this pointer if you wish. And in this way, you can't really write into that memory. But if you're really interested in what your computer stores at address 0, which is probably very important information for the operating system, then you can read it with the help of a pointer. That you can certainly do. All right. So this is, one thing that there's about 10 slides left for today. This is not a problem if I don't go through all of them. But one thing is really important also for one of the homeworks, and that is you can look at arrays of strings, which combine pointers and arrays of characters. And what is a very important example of this is command line arguments. These are 0 or more strings that are specified when the program is started. Suppose you have an executable program, let's call it SEQQ, then all the programs that we have written so far didn't take any command line arguments, so we've just started them as a.out or RBT. But you can also give it command line arguments, and these can be read by your C program. The way this is being done is, this is how it would be represented internally. You would have a value argument counter, which gets the value 3, which is always 1 plus the number of arguments, because you can also access inside the C program the name of the program. And what you do have is an array that points to the 3 strings that are given as arguments here. So even numbers will be interpreted as strings, and they will be interpreted as 0 terminating strings as usual. The internal representation would be you have an array of pointers, and they point to these 3 strings. Now, I just have 30 seconds left for everyone who's listening, and I promise to always be on time. So please do, for the homework, look at this slide here, how to access these numbers and how to convert them to actual numbers. And look at the solution to this exercise, which shows you how you can read command line arguments with the help of a main function. Use that for your homework, and with this I will end today's lecture and continue at exactly this point next week.